So we're jumping back in, and I think Adrian said something to this effect the last time we met, but we're sort of going to specialize in two different directions. So Adrian, when he's presenting, will focus more on the numerical applications or numerical methods.
Yeah.
Okay. Whereas when I'm talking, I'm going to be moving more towards the differential geometry setting. So today, the point is to set up the setting, get a few prerequisites out of the way, and then try to say something interesting. So, say, stochastic differential. And also, of course, I feel obligated to do some shameless self-promotion. It won't happen next semester, but I believe 2 semesters from now, I, in association with Ireland, will be giving a course in stochastic differential geometry.
When?
Not next semester. I hope 2 semesters, but if not, then
Next 3 Christmas.
yeah, it could be.
Nice.
This is part of the GeoProco.
Yes.
Yeah, so Ireland submitted that we'll do this, and my understanding is that if I want to, I can run it. So probably. At any rate, to start, beginning here, I am using with permission Anton Hamaye's notes. The name of it is running a variety of motion. So these are notes that he makes publicly available on his website, and they are absolutely excellent. So we're going to be following these, at least at the beginning here. And I think our goal for today is to get through the first chapter of these notes. So what is our setting? We're going to be working always in the category of smooth manifolds, and usually Riemann manifolds. So this, of course, gives us the question. I'm not sure how much of this I need to recap for everybody to be comfortable. So are we okay with basic definitions for this? Yes. Yeah, okay. So always, everything we do is a smooth manifold, and I will without comment, use a Riemannian structure, although some of the results hold when you don't have the Riemannian metric. All right, so then in this case, what I'll start with is talking about the tangent model. This is a quick reminder, because I mean, this should be familiar, TM in the projection on the manifold M. And what this means, we can take sort of the abstract definition coming from differential geometry, that TM can be seen as the disjoint unit of TXM for X manifold, where then we have the projection it's always the same. This is the simple definition.
Why should we stop this union?
Disjoint union, just to say that
Disjoint union.
Yeah. And I guess I can make the comment that n-dimensional, then CXM is always essentially. The isomorphism is non-canonical, but you can think of it as saying that we are taking the disjoint union of copies of Rn. And then we can take a definition of smooth sections. So a smooth section of a tangent bundle. Yeah, I can say this. Is instead of maps, we go from the manifold into the tangent bundle such that the projection of A evaluated at, let's say this. So this is probably the cleanest way to write it, but I mean, basically what we want is that we have compatibility with this structure. What I'm saying is that if you pick some point, if we evaluate A at X, which is right? This should be an element of the tangent space, and in particular, the projection of this. This is okay. I think this is all probably trivial. And I think it's smooth. Which is to say that it agrees with the differential structure of the manifold. So what is all of this? Okay. So if you remember some differential geometry, there are non-equivalent definitions of vector fields. So this here is somehow the more abstract definition that we usually take once we're okay with bundles, things like this. So I can also just remind us of some other definitions. So we can say that HP equivalence classes terms. So I'm going to leave this sort of imprecise because I'm not taking into definition. But what I mean is that if you look at curves, yeah, some interval from real line into the manifold, smooth, of course, that we can take equivalence classes of these by their differential, and the equivalence classes of curves like this that pass to the point is actually the definition of tangent space at the point. Yes, yeah, exactly. So by the equivalent up to the same derivative. Exactly. In this case, it makes taking this definition makes it a little bit easier to see then that the smooth sections of this are derivations of C infinity. So what I'll say, so I'll write this to mean that taking that as a definition, but we can see this as somehow equivalent. It's the so maps from smooth functions on M to smooth functions on M that are linear, and derivations on the space of functions. That is that A of F G equals F. A of G plus G at F. And I know the notations of differential geometry can get a little obtuse points. So what I mean by this, I mean that F and G are smooth functions. If you have two smooth functions, here we're talking about the product of functions pointwise, and this is seen as an operator. Actually, that's what that is. Here, this is again the product of functions. So A of G is a function multiplied pointwise with F, and so on. So, yeah. Sorry.
If you're repeating finite dimension manifolds, this is fine. If it's infinite dimension, I think we need to require also this A to be a logical operator.
That sounds right, yeah. So we can make this comment, everything we're doing is finite dimensional. Yeah, there definitely are extensions to infinite, but not gonna mess with that. Okay, so yes, so I say that this is somehow the space of derivations, and yes, okay, we can write this as well. So then we can set that A acting on F at the point X. If you want, I can put more parentheses, but I think will suffice. So what I'm saying is that this, disregarding the smooth function now, is actually giving a definition that would be differential of F in A at X. Okay. So what do I mean by this? This feels extremely redundant. So this I hope makes sense over here. df should be regarded as the differential. So that is a map between tangent spaces. In this case, it's a map from the tangent space of a manifold to the tangent space of R. Well, tangent space of R is a copy of R. This, well, it's acting in the tangent space, and then we evaluate all of this to get X. Wouldn't make sense for these points to be different, but we need to repeat this. So, yeah, we have this sort of do I want to mention this? Yeah, so let's talk about local expressions. Yeah, that's unfortunate. I ran a little bit too far there. Okay. All right, so let's say we have a local chart. So just a reminder what we mean by local chart. That is that U is open, and H is a map from U and smooth. And moreover, that there's a compatibility condition that if we define two charts that on their intersection, they have to agree in the sense that if you take a function from Rn, pass it backwards through one of these charts, and then pass it forward to the other chart, we must have a diffeomorphism of Rn, always. Anyways, so we have some local chart. We can find vector fields dh1 through dn by pullback Rn. So what I mean is that you take the standard unit vector fields in Rn, pull them back to the manifold of this chart.
Can I
Yes.
comment on there? When you write dfx is a map from the tangent space of x to R, right?
Yes.
So it acts on the A restricted to x. It just makes more sense to me if the x was then tied to the A instead of outside.
Yeah, you're right. I should do this way.
Something like that.
Okay. Yeah, sure. Let's agree that for vector fields we can use subscripts to do this.
Yeah,
So sure. Yeah, you're right. You're totally right. I agree. It's better notation. Okay. I'm just mentioning this because I want to say that we can always, right. Then A restricted to U can always be seen as a sum. Okay. So we can always get local expressions of these things. And doing differential geometry, we like to avoid this. Our goal is trying to get away from this in some sense. But it's important to know that we can always do this. So then, now that we're in the setting, I'm going to briefly write things the way I think Van should have said a few weeks ago to try to explain how we're going to use this to make sense of an SDE. So to do that, we need a vector field. So yes, let's say we've got some curve. So given what I do, and some x, I'll call it x, not in the manifold, we can actually define a flow. Curve xt. So that's, let's say, yeah, from some unit interval r to the manifold. Let's say, we say the curve xt is the flow generated by x via a. If we can say that x at time 0, yeah, I should be. We have this thing where we skip back and forth between subscripts and not subscripts sometimes. So for the moment, I'll write this as not subscript. This is my initial point, and that x dot at time t should always be a. Yeah, moving back and forth between subscripts and subscripts is a little bothersome. But what do I mean by this? If we think about this on an Rn, and it's just Rn, all we're doing here is solving a differential equation. No DE. No DE or n, or n is the dimensional space. So this is really just a generalization of this. And if we have this, it's going to work exactly as it would for ODEs. By expressing things in local coordinates, we can solve this locally, which is to say that we can actually solve this on our end in local coordinates. Yeah. So what I should probably say is, instead of saying flow, I should say the integral curve. Yeah. It's sort of a back and forth in what we mean in different words here, because then what we say is if x of t is an integral curve, right? We define flow phi of t, which is going to map from m to n by pt of x is equal to x of t, where x of 0 is given by x. So what am I trying to say here? At this level, if you pick some initial point and you can define some curve that starts at that point and its tangent vector is always given by the vector field value at that point. This is a curve that is a solution to the differential equation given by A. That is, it's always tangent to the vector field. Down here, what we're saying is that I want to define a map, so from some fixed time t, that sends the manifold to itself. And it does this by taking some value and treating that as the initial condition of this. Is that all right? It's a little different here. All right. So we work with these sort of flows a lot. And the consequence of this so we can say is that we take any smooth functional manifold that is compactly supported. So its support has to be contained in a compact set. That derivative with respect to t composed with the flow It's always going to be equal to A of F opposed. So this is a nice way to see this composition. And I mean, we can also say,
I don't think it's a definition on the derivative of that. Depends really on that.
sure, yeah. I mean, in this context, we can really see this as a map from the interval in which t is defined to r, right? So this is actually just a regular derivative. Because we're seeing, we should see that f of p of t is really a map from I to r. So this is really just regular derivative. And I mean, this, then we can regard this now as a function of that, right? And we also get the value is 0.
The complex support here, does that mean that f is equal to 0 everywhere outside of a complex subset?
Yes. Yeah. So yeah, we'd like to do this on large just smooth functions in general, but if we don't have compactness of M, there could be some issues with things at infinity. So yeah. I mean, often in applications, M itself is a compact manifold, in which case none of this really matters. Well, other than distinction, it doesn't matter. Not none of this. Yes, this is fine. But yeah, okay. So if you want, you can take this as a definition, and what happens is that this relation somehow follows from the chain link. This is sort of equivalent here. But what I want to point out, and this is the part where it actually matters. Whether you take that as a definition of this or this, however you do it, the end conclusion that we will have is that f of t evaluated at x minus f of x. All right, and then the way we want from the interval from 0 to t. F is not f, so we're looking at this right here. Yeah. Goes with phi of s. Yes. So if we have this expression here, it always vanishes. All 0. Yes, okay with this statement? I mean, this is essentially rewriting this differential level. Okay. The point is that all of this is pretty immediate as soon as you understand that we take a manifold, we write it in local coordinates, and then all of this just follows from the regular theory of ODEs. There's nothing fancy happening here. But the reason I go through all of this is because this expression is how we're going to make sense of the flow of the second order differential operator and how we're going to recover stochastic differential equations on manifolds. I don't know if this is the right point to make the comment, but it's also possible, if you want, to try to understand stochastic differential equations on manifolds as a solution to some sort of projection. You can use the Lee-Whitley embedding here to say, take your manifold, put it in Rm for m large enough. Do stochastic differential equations on Rm and just project it onto the manifold. But if you do this, your projections are, they're not canonical. You can have many different ways this could fall out, and you can get non-equivalent. It's not clear that your results are equivalent, although you can work through it. So we're going to work from this perspective, so that everything is somehow intrinsic, and it's clear that we get, we have somehow, what was I, a definition that doesn't depend on your embedding to some bigger space. Okay. All right. We also, just as a little bit of setup, we define PT. How do I want to say this? Let's say that it takes these two functions with compact support into some functions here. You want this? Yeah. Sure. By T of F. Okay. So you can sometimes this, depending on context, this is called the heat operator given by the associated to A. The point of this,
Just a pretty regular function.
I'm sorry?
It's just a pretty regular function on the project.
Yeah. Yes. So notice then.
It's really nice one here. I have to feel one that is bothering you all the time.
Yeah, and asking the questions and clarify the sort of nonsense I'm saying. Yes, perfect. If you take the derivative of this expression with respect to time, wait, no. There we go. So, I mean, you can see this, I just integrate this expression here. Okay. So, what's the point? Well, in particular, if you know that it's 0, PTF, divided 0. What do we get? PT is 0, is F of phi of 0 is F. Yes? I should write parentheses. Okay. What this means then, the way we interpret this is thus from knowledge of the flow, we can cover F. This is the sort of way to do this. There is a broad generalization of this idea, but for our purposes, this equivalence is nice. So what do I mean by equivalence? I mean, given a vector field A, we can define this operator PT, and given PT or the flow phi, we can recover A. So a back and forth equivalence. Yes.
And then you can say about one parameter families of all these models. That's the second flow is this.
So maybe I can write this.
I can show that if you go over.
Yeah, no, this is exactly right. I've seen it presented in a course that was focused on a little bit different aspect, but there is then somehow an equivalence. Yes. So to see this, really what we did is given A, we define phi of t, we then define phi of t, and then we recover A, which then makes these all equivalences. Okay. So yeah, I've heard this labeled the so-called golden triangle. Fabrice Boulon said this. I don't know if he got it from somewhere else or if this was the name that he gave to it, but I really like this. But in that context, A is more general. So right now we have this for when A is a vector field, which we can also regard as a first order differential operator. Yeah. All right. So I think that's an interesting statement that we have this sort of equivalence, but we want to get past first order. Right? Everything we just said is pretty straightforward. once you're okay with ODEs. So what we want to talk about now is what the A is sector. So let's count. Okay. Tangent space, that is, yeah, sure. Okay. So we take this as somehow a definition of second order differential operators. We interpret this as, I would say, we interpret A squared as A squared acting on F is equal to A acting on A. Yes, well, this all makes sense because A acting on A and acting on F is just composition of operators. Okay. There is something a little subtle that is sometimes surprising with the differential geometry here. Where is generally not. It is clearly a differential operator, right? But it's there's several different ways to see it can't be a vector field. The easiest, most direct, is that it doesn't satisfy the definition of a derivation. It won't follow a chain rule or just product rule functions. You can verify that directly. Yeah. Okay. In fact, I write generally there. I think I could probably just make the statement. It's only a vector field that distribute. A little bit like this. So we somehow now want to make sense of the flow generated by such an operator. We cannot try to think of the idea of a curve of x such that x dot equals L for the aforementioned reason, because a squared is not a vector field. So thus x is x dot, I don't know what I need to do with x of t to L. Something like this is not simple. Right, because x dot is necessarily a smooth section of the tangent bundle along the curve. It's restricted to the curve. It's lovely, but it can't make sense. So we jump back to that second definition, the one we were talking about, where I said that the difference of f of x of t and f of x can be equal to the integral of that. We should make a comment before we do that. Yeah, that's probably the best. But we can do this in local coordinates. So, chart HU. We can always write L restricted to U will be given by some notation like this. Yeah, of course. I'm also going to shield a little bit and give you some notation values for the rest of the time. Maybe less than, right? No, I'll shield it. All right, so to explain what I mean by this, I is just shorthand for UDHI. The advantage is that I don't have to write up coordinates I mean, because we're always just working in one coordinate chart. So this is a notation. I'll make the comment, and Aij equals Aji. This always happens. So yeah, first one is a notation, but this is actually a consequence of definitions. If you want to know why it's symmetric, what you do is you can imagine writing this out in two non-equivalent ways. Take some sort of symmetric difference, and you'll see that it falls out. This has to happen. Because what happens is when you take the bracket of these two, if you take the commutator of d and dj, it's always going to be a vector field and fall down in this order. Okay. That's all right. Okay. Maybe I'll write it really well. D I D J D I. Okay, this is just a notation. Is so its coefficient would actually follow as some other I necessarily. Is there anything else we do with this? No, this is fine. You can, if you want to be clever, you can then write this as a vector of the i's and print aij as a matrix. It's nice. Or you can see it in the two times over, however you want. If we're working in the context of Riemannian geometry, you can see this is a 2-0 answer. So what? Yes. So we'll take this as a definition. And so let omega f, putting of information, and measure, and then initialization. Fine, yeah. Okay. Oh, this is- This is coming from course, and I can say adapted if you want. All I mean by this is that the filtration is adapted to measurable sets, as we defined. Yeah, okay. And that's x. X. T. Writing x t x 0. This is just a notation that I don't think we've used yet, but the point is to abstract. The point of this is to abstract away from time. So we want to think of x. Right. Be a random variable for each x and x. Yeah. So what do I mean by this? I mean that if you pick some point in the manifold, we have this object, which of course varies with t, but it's actually a random variable, so we of course suppress the fact that it takes out an omega, or it acts on omega probability space. And we needed to take with values in R. Is it clear what I mean by all of this?
Yeah, so.
So if you really want to be extremely precise, you could say capital X is a function of time, the probability space, and a point in the manifold. Okay. So in this case, and I should say I'm not going to write it. It's adapted to this filtration. Then give myself more space to give the definition. for a given differential, given second order PO L M. We say X dot is the flow associated L. If, very nicely, N P F X given by F of X T of X of X minus the integral from 0 to T of L F evaluated at X S of X S is a, if we want, yeah, okay. RDL for all compactly supported functions. All right, so let's break this down just a little bit. What's going on here? So I'm defining stochastic process for given point X by this expression. Everything in this expression makes sense, and it is, well, just another stochastic process for a given X. Given X and a given compactly supported function. If A were a first order differential operator and X was deterministic, this would equal 0 precisely when xt is the flow. We're okay with that? That was the expression I put in a box over there. So we want to generalize away from that. And I said we can't do this for some deterministic process X. It's just not going to happen. So we wouldn't expect some sort of integral expression like this to hold if capital Xt is a deterministic flow, which again can't happen for the equivalent reasons. So what we've done is we've pulled this back to the level of stochastic processes, and then well, we're not going to expect some stochastic process to always equal 0, right? That's not reasonable. But we can ask that it's a martingale, which is to say its expected value is 0. That's the idea. So we generalize away from flows to stochastic processes such that their expected value is 0. So all right, that is the expected value of NFT of X. Yeah, it was oh yeah, and of course I should make the comment that I can only make this expression make sense if we're talking right now, given what context, if we're talking about random variables on Rn, which is why I have to include function f.
You have to work on Rn? No.
I'm saying this poorly. No, this is fine. The way this is fine. So if you fix some x in the manifold, you can see NFT. It's fine. As just a stochastic variable taking values in R. So basically, by putting an x here, we're almost ignoring the fact that we're working on a manifold. That's the idea. Yeah. So this is our definition. We call these, unsurprisingly, test functions. Okay. So where I won't say any of this. I will say, what happens immediately? I'll make a few quick comments and then we'll take a break. When we come back, we'll see about some interesting tools that follow from this. Because I should say that, I mean, the last time we met was what? So last week was good, before that we canceled. So 3 weeks ago, Adrian spoke. I think what he said was on some level very equivalent to many of these statements.
We worked on the generator,
Okay.
will be numerical analysis part, it's the same generator.
So up to the fact that I'm working with functions that are defined in manifolds, it's equivalent. Yes. Okay. But we're going to get into some new things after our break. But I will just make some comments on how to work with this. Okay, so if we have a second order PDO, we have the flow associated to it. The only thing we're missing is the PT, right? So we will go ahead and say then we define PT acting on some functions. It's a little redundant to write this. Make the compact for safety. T F evaluated at point X equal to value of F at X plus the integral. Well, let's not take this as a definition. I think this is the form. Where is expected value? Expected value of F of X. So this is equivalent to the definition for PT for terminated flows, except that I stuck on an extra expected value, right? Because we don't want PT to somehow be a random variable. What this accomplishes for us now is that if we have some starting point, we can determine based on a compactly supported function f a diffeomorphism essentially of the manifold. And this tells us something about the way in which this behaves.
If I understand this, the low goes.
That's a decent way to say it, yeah. I like that. And then just really quickly what happens with this should be clear. Yeah. That PTF evaluated at X is necessarily equal to an expression of right. Acting at X S of X DS, right? This follows from the martingale property. And then take the derivative of this. T of PTF at X, yeah, at X, of course, is, well, this disappears. Derivative. We're going to just put this in here. So we're going to have the expected value of LF of X. Long parentheses is PT LF X. Right? I mean, now you can see this is a direct analog of what we had in the deterministic case. So evaluating at 0. So, right. 0. 0. Let's put the opposite direction. So I can say this. Sure. The expected value of f of xt. That's okay. Which is essentially expected value of loss expression. Okay. So this, again, basically the property. This, taking the value of this, put this at 0. We know at 0, we get to have the identity map. So, in the same way as for a deterministic process, knowledge of PT recovers knowledge of F. Which is all we can hope for, right? I mean, this is nice. But I mean, and how do I say this? This expression says that in the same sense, the stochastic process xt, the operator pt, and the operator L, again, have this golden triangle relation. If you know one of them, you know all of them. And I think at first glance, it's a little surprising because xt is stochastic. but the level of expected values, we still recover the same kind of information. Yes, so let's take a pause here. When we come back, I think we'll go over some examples, and then we're going to introduce some tools for working with these that don't show up or haven't shown up in our course before. Okay, great. So a quick correction to what I said before, which I think was clear from context, but I also need to say it. Xt needs to be random variable taking values in M, not in R. So I can write this explicitly. So we need Xt, which is also, of course, a random variable. We're suppressing the notation to that. Great. So yes, let's begin with a handful of examples. There's some really nice ones in here. The first one, product showing, right? So yes. Let n just equal Euclidean space dimension n, and L equal half the Laplacian. You say it's the differential geometers Laplacian if you want. The 1/2 essentially falls out from the fact that we need the symmetry of the second order vector fields. Anyways, we're running with this. Okay, then and right. So xt so implicitly we have a filtered probability space. That's part of what we mean by Brownian motion. So we can say Euler's formula, which we discussed at length. We have that. Compact stuff. We're writing at the level of differentials. We of course have expression. I'm using the shorthand. Yes. This. Yes. Okay. So what have I accomplished here? We're running out the Euler's formula, and this 1/2 accounts for the fact that we need to have symmetry here, right? But otherwise, this is just Euler's formula, equivalent to it. Let's think now what happens if we regard Rn as a Riemannian manifold, where we have the standard dot product. Well, in that case, the sum, the first partial derivatives here, is just the gradient of f. So I can write this. This is the gradient of f against f. Where we want to see this, again, level of differentials. So when we integrate against this, we're integrating against this expression. Of course, when let's see. So we do that. Yes, there. That's what I was looking for. Okay, so what happens with the second one? Well, when we have a set of second partial differentials, of course, we just have Laplacian. So we have plus Laplacian of f evaluated at t. Recall here, I'm getting the dt because this is being thought of as level of differentials, but we know that as a rule, whenever we have this because of quadratic variation of gravity motion. We're always going to get dt. Okay, cool. This is great. But what does this mean? I mean, if we just reinterpret this in one iteration, expand this out. Plus f of x minus f of x0, which is all right. But you know what I mean. Of course, if this is deterministically given by a single point, we then move this expression over and realize that the level of integration just has to disappear. So we get minus, I'm suppressed, that's right, minus the integral from t plus of f s, yes, this is a particle. So what do I mean by this? Well, if we take the expected value of this, it's going to be the expected value of the integral of this, which then vanishes. Yeah. So the conclusion, of course, is that so x, the x is being equal to the initial point plus notation's here a little bit silly, right? This is going to be thought of as the flows that we were defining before. This is the Brownian motion that I picked at the beginning of the problem, the lower, whatever. Is it occurs to me that I didn't use this term. The word diffusion here is the name that we associate to the flow associated to differential second order EDF. All right. Is that right? I can't remember. That is the definition. But this is what I mean. When you have xt, stochastic process that satisfies this definition I gave before, we're going to call xt diffusion associated to L.
There is, I'm with you, the transition from that one to one bottom. There is something about expectation within the productive series and so on.
I'm sorry?
When you have the conclusion from the second line, from there to there, exactly. What was the argument there?
Okay, so what I do is first I subtract this term from the left side.
Yes.
I evaluate the little integrals. So this becomes f of x minus this minus the integral of that expression.
Yes.
This is essentially, this is a stochastic process.
Yeah.
If I take the expected value of it, it has to equal the expected value of the integral of this expression.
And that's 0?
Yes, because this is
X is just a shorter version.
Yeah.
In simple example. Zero is long.
yes.
To the next chapter.
Yes. So we're using the fact that x is a Brownian motion. This is a good book. This was a good.
That's good.
Sorry, it's a good point. Skipped over that. But yes. Okay. Yeah. So I mean, this is just a silly statement. But let me make a comment here about stopping times. So we glossed over stopping times before. They do become increasingly relevant when we move to differential geometry, especially in context of existence and uniqueness theorems. So I should say something about it. Yeah. So we know that even for existence uniqueness of solutions to stochastic differential equations on a RF, we can need stopping times to show up. And the reason for that is that we can have blowups in finite time. So we talked a little bit about that. I forget what the strongest form of existence theorem we made or uniqueness theorem. But for solutions to stochastic differential equations on RF.
Yeah, it's the
Did we-
limit is if existence unique on the fixed interval.
Okay, so we did fixed intervals. Right? You can expand this by talking about stopping times, which I know we did a little bit of, but so I'll say this. Okay. So yeah, okay. So on manifold, what we're gonna do. Wants to consist What we define and all right. So what do I mean by this? So if you pick a point in the manifold X, which again we're thinking of as our initial condition, tau then would be a stopping time. That is, it's a adaptive random variable that you can measure the event whether or not it stopped. There goes a little bit. Okay. So then we'll say is that that is we want X not only to be restricted to the terminal 0 out of X. That open. Okay, so we can have this open interval and where we have the event out of X is finite. It's going to be a subset limit as t increases x t omega equals infinity in hat is okay. So what do I mean by this? Because this is where a little bit of subtlety comes into play. So by stopping time, we mean that we want to be able to measure this event, and it's important to understand what our stopping time is infinite or not. So we want to insist that our stopping time is almost surely finite. But more than that, we want to actually go ahead and yeah, exactly. So we want to say that this event is always measurable compared to the event that for some omega, it actually explodes to infinity. So what I've done here is that I've taken the manifold and adjoined a single point, which we call infinity. This is the one-point compactification, or Alexandrov compactification. Yeah, we want to somehow control when this happens. All of these considerations become a lot simpler when we insist that the manifold is compact, but it's nice to get some statements.
Why is it that you need to do something special for version? What was the sort of restrictions lacking compared to RN?
You need these considerations on RN as well. So if you have it's just that the difference is the definitions can be a little bit simpler because we don't need to talk about one-point compactifications. We can talk about like exit times or arbitrarily large balls, whereas we don't have quite that much structure. So to make it, this is just a way to make that make sense in context of non-compact manifolds. That's a good point. RN doesn't all have this. It's just you have to say it differently.
But this stopping time, tau of x.
It has a name, yeah.
One like that number is a real number determined by point x.
If you can find it, yes. So it's not a number, it's a random process. It's a random variable itself. But yes, for a given omega, it's a real number.
I intuitively think of stopping time and you put some boundary around things. So KS stop with a boundary.
Yeah, that's so yeah, you can think of it that way. You can think of it as saying that if tau has this property, that is, it's contained in this event, that it's somehow a maximal stopping time. It measures when the process would somehow escape to infinity. Yeah, that's the idea. So, and if I call this we'll say stopping time satisfying star is a maximal. So, I mean, just to give you an idea, a lot of proofs will often work with saying, let tau n be a stopping time, or some stopping time that's not necessarily this, and then such that as you increase in n, the tau n's increase up to the maximal stopping time.
So this stopping time is moment, it describes the moment where the solution is closed.
Yeah, basically. So you can think of it this way. If you have a maximal stopping time,
Yeah.
there should not be a way to extend beyond it. But you can have a non-maximal stopping time. You just stop the process early.
But why isn't it needed enough? Because
Why is it what?
it's not needed enough as well. We don't care. And
I mean, it is depending on the process you're working with. You can have processes that blow up in finite time.
yeah, but like I have a parabola, why my solution is moving on it. Why do you need this stopping time? It's just for the theorem to say, okay, it exists.
Yeah, this is all going to be used for existence and uniqueness terms. This is like if the stochastic process could explode in finite time, then we have to define it. Well, it's only defined up to a stopping time. So that's a statement of an existent statement. Yeah. And this definition essentially allows us to say that any stopping times must be controlled by this one. This is a maximal stopping time. That make sense?
Yeah, and can you add some assumptions on the generator so that you don't have to take stopping time? You can just take any finite.
It's not just about the generator, but the manifolds.
Okay.
Yeah.
Thanks.
Yeah, okay, sometimes they call this a maximum lifetime for the process. Maybe I can write this then. The relative context is, yeah, sure, we can say this. So,
Simple stochastic differential equations blow up in finite time.
yes, yeah, absolutely.
For non-stochastic, you need at least something non-linear to blow up in finite time, but you don't need that.
No, even a linear ODE can blow.
Sorry?
Even a linear ODE can blow.
Linear ODE.
It depends on, yeah.
Yeah, the ODE. Yeah. So this isn't unique to second order or to stochastic or anything. I had a convenient example. I never wrote this out. I think it's here's y3 equals 1 over y minus 1 y of 0 equals 0. Solution to this will blow up at time 1.
See, but usually we make assumption of the generator because we say the functions that are involved are dictates, and then everything is fine if I maintain undefined interval. Can we do this here, or is it depend on the manifold?
I think it's necessarily dependent on the manifold. Yeah.
Okay.
So I think that the typical approach to this is that I was going to write a little bit about this. You have some sequence of relatively compact subsets of the manifold, and each one of these you can do exactly that. You can control it by you can control blow up times by conditioning the unknown.
Okay.
But then as these compact sets fill the space, you can't always do that. So I'll write this. So what we can say is, yeah, so that's UN open relatively compact. subsets is UN is a subset, shall be proper, of the closure of UN is this one, right? And then we go all the way up to yeah, and union across N of the UN. All right. So if you have this, then what you do is define first exit times. Zero, I don't know, U1, where do you want to start? Say zero. It's unambiguous. Yeah. By tau n x equals equal the outside infinite zero such that x ranging from x is not in. Okay. So all I'm saying is that we have some sequence of space of relatively complex sets to fill them, and you go ahead and define first exit times. The first time the process leaves this set, right? Then what happens? Then tau will necessarily be the supreme across n. So tau here being maximum lifetime. Make sense? Okay. So this always happens, and then what we're going to do is, in order to get uniqueness results on these stochastic processes, we're going to want to, we're going to need to define them on maximal lifetimes. So we work at first exit times and build up a maximal lifetime.
Did you say relatively complex?
Yeah, this is just to say this. So because UN is always it's a closure, but then the closure of UN always needs to be inside US+1.
Okay.
Yeah, this is that's all the compact really just means this.
Okay.
So what should I do? Yeah, okay, I'll say this. So generally, yeah. Smooth, and because we're working on complex sets over here like this, we actually don't need to insist that F is compactly supported. And Fx, remember we defined before, so I should put the dot right here. Generally, okay, I don't know again. Local. That is, yeah, this is the stopping times. Yeah. And switch that. And which so what I'm doing here, I'm trying to adjust these the same problem lower times. I'm saying that if we have a generator and we have a diffusion associated to it, I shouldn't say that. If we have a generator we're gonna have problems finding diffusions for all t. So what happens instead is that we stop it at some tau n. Then we can find solutions xt such that the stopped process of Tn actually is a martingale. Does this make sense?
I'm not sure. What is the Europe there? T.
I should say this, T image, so what this does is that when we're before the stopping time tau n, we're just flowing along t. T is presumably normal. But when we get to tau n, whatever it is for this event, it stays fixed.
But
So then, so yeah, this is a kind of a silly way to word it. But what I mean is, we're going to have an operator. We're going to want to find diffusions associated to it. And doing that for this can be a problem. So instead, we go ahead and stop the process at some tau n. And this will be a martingale for an entire sequence. And then we let the sequence increase up to the maximal time. That's how we show an existence result. So we'll have existence up to some maximal stopping time. Yeah.
with NF of X.
This was the definition I gave before. Is the f of xt minus f of the initial point minus the
value.
Huh?
Is a real value, or is
Yeah.
it?
Yeah. Yes. Yeah. Because we're evaluating f on the process. Like,
Yeah, I remember.
This is just some technicalities to the existence results, but they do matter. Yes, here, this is an interesting statement. Why does time go so quickly? Okay, I'll make a statement. I'll give you a preview of what I'm going to say. We proved next time. I'll write it this way. F of x t. Hopefully on generation. For any if and only if L is so this is maybe not surprising in light of the way I try to introduce diffusions associated to second order PDOs, right? Because I made this comment that it really shouldn't be possible to expect that we would have a curve, right? That we'd have some curve that would be everywhere tangent to a second order PDO, right? Because it's not in tangent space. But we actually have an exact equivalence that we could expect that the diffusion associated to some operator and pushed back down to the real numbers will have bounded variation if and only if the generator is actually a first order. So this is an exact statement, and equivalently that is so. This is the same thing as saying L. Yeah, I think it's really obvious, really clear that if it is for the first order, of course, would be bounded variation. I mean, this is we're just taking regular intervals or something. Going the other ways won't necessarily be the other ways. Okay. Yeah, we have several nice examples, but I think I'll take 5 more minutes to introduce something nice. The tool that I'm alluding to that we're going to use basically here going forward to be able to work with examples, to be able to prove statements like this, to be able to talk about existence and unique results, and it's a really cool tool. Definition. That's to CM, the linear map, I should say our linear map. So of course, the motivation is second order PDOs, but I mean, everything's going to hold for exchange order. And there is a lot of study into this, what happens at higher order. And it's instructive to think what happens at first order. We define. I'm trying to shop. I spell it properly. Yeah, but yes. Operator. To and I wanted to point out, or this sort of awkwardly, it's a bilinear operator acting on smooth functions by gamma on f g is going to be equal to 1/2 L of their product minus f LG minus G LF. So, what does this accomplish? 1/2 here is arguably an artifact of differential geometry. This is the same thing as measuring and passing on the velocity, so that's not so important. But think about what this does when L is the first order start. First order it satisfies regular product rule. And thus, right? I mean, it's just getting rid of product rule, getting rid of the product. Think about more generally. If L is second order. So then you can say, local charge. What's right? So we have some, I'm not going to write the summation specific time. Plus double sum J. Yes. I should say second order and no constant. Depending on how you take your definitions, it's not obvious, but yeah. What do we have? Then G coordinates the sum J S G J G. So maybe it's good to take it out, take a second and write it out. But this term, of course, finishes the same way it's using the definitions. If you write this out, well, what's going to happen? So when you act on the product FG, you're going to get terms that have 2 derivatives in F, 2 derivatives in G, and then 1 in each. And these will count the terms that have 2 derivatives in G and the 2 derivatives in F, thus canceling. So from this, the only terms that can survive are the ones that have 1 derivative in F and 1 derivative derivative of G, which is precisely what given by this. The 1/2 disappears because we're taking advantage of the fact that A I J is symmetric. So we don't have to, I mean, we can write it out, the 1/2, and then we have I and F, J and G, and then switch it, but we don't need to deal with this. That 1/2 means we get this nicer expression. Yeah. Okay. So already you can see, so in some sense, gamma captures second order information. Properly, we should write the fact that gamma is associated to L, and if it's ever confusing between multiple operators, we use this as like a superscript, gamma, super L, or something like that. I think it's interesting to also think about what happens to higher order differential operators. You can write it out, it's kind of a cool thing to see. But as a final comment, if M is simply Rn, L is the 1/2 of Gaussian. Actually, I don't think the 1/2 in this case because of that. Then what happens here? Gamma of F is the magnitude of the gradient of squared. So if you want to see this, anything with Laplacian, these are all, these are the delta functions, right? So 0 if I is not equal to j, and 1 if I equals j. So when I equals j, DIF is this. If you want, I could be a little bit more technical, like this FG is equal to this, the Riemannian dot product. Yeah. But somehow I think this fact is a little bit more interesting. So yeah, I think this statement clarifies this a little bit. So in some sense, gamma is capturing second order information, but also we can understand that if L is second order, then we have this relationship with the first order derivatives of F. Yeah. So anyways, it turns out that understanding the Kite-Duchamp operator is absolutely essential, some deep way, to being able to understand, work with diffusions to second order operators. The deepest relation we're going to see is that the Kite-Duchamp measures the quadratic variation. So we talked about this at the level of when you're taking the EOS formula. Second order is going to be against the quadratic variation of the process. Yeah, the Kite-Duchamp captures this. But anyways, yeah, I'll leave it with this. Next time I talk, I don't know if it's next week or 2 weeks from now, we'll see a couple of examples. We'll take a look at the Dirichlet problem, the heat problem with this, and then we'll get some existence needed for results.
So next week is numerical analysis.
It's totally your choice. It's totally your choice. I will be ready to present the part 2 of this, but if you have some reason you prefer to, you can take next week. It don't take 2 weeks.
It's fine.
Yeah.
You are not following some of those stuff that that was 1 year old at the beginning.
Yeah, I'm using that.
About 5 days.
It's on Tomai's website, but I can send you a link as well. I can just send it out to everyone. Yeah, they're really nice notes. It's he taught a course for masters and PhD students in solving PDEs using SDEs. Yes. But yeah, I think it's a better starting point for us here that we have a background in SDEs.